It's the one on page number 6 in the second chapter of lecture notes. It says, given two vectors, A and B like this. Given two vectors, A and B like this, we need to find a third vector, x, three-dimensional, with the conditions that it is unital. And if you never heard this term before, unital, it means that the length of the vector is 1. So the vector should be unital, and it should be perpendicular at the same time to A and B. Yes, to A and B. Having dot product, solving such equation is a very easy task because when they say find the vector, they mean find the components of that vector. So the first step I do, or the first step you will do when you recover the full length of the solution, you will introduce the components, unknown components for your vector, x1, x2, x3. This time you see I go non-conventional way. I don't use x, y, z. I alternate notations. So x1, x2, and x3, the components. And then what you do, you just express this condition in terms of the dot product. In terms of the dot product, we know perpendicular vectors mean that the vector shut up. Perpendicular vectors, it means that the angle between is 90 degrees, which means that the cos is 0, and the test therefore is just dot product of two vectors is 0. If you compute the dot product between these two vectors in terms of the components, it will be two linear equations. So here's what I just said. Here's a line symbolizing that. Perpendicular vectors mean that the theta angle is pi on 2, or 90 degrees, which means cos is 0, and which in turn means that the dot product of 2 is 0. This is a very powerful orthogonality test for vectors, which, by the way, after we establish with you the Cauchy-Schwarz and all of the implications of that, which, by the way, also works in higher dimensions. So if you express this orthogonality test for this statement and for this statement, did I do that? Yes, I did it here. Here is the dot product of x and the vector A, isn't it? 2 times x1, negative 6 times x2, negative 3 times x3, and that should be 0. That's the orthogonality test. And the dot product for the other pair, x and b, here it is, 4 x1, 3 x2, and negative x3. Here it is. You're looking at the two equations with two unknowns. And there is a way to solve that. There are plenty of ways to solve that. We haven't studied in general how to solve system of linear equations, 3 unknowns, 2 unknowns, any combination in fact. So I suggest you will use some sort of ad hoc solution. So I'll suggest you take one of the components 1, say x3 is 1. Again, don't ask me why yet. The explanation is coming when we discuss with you the system of linear equations at great length. You will understand why this happens, but my intuition right now suggests, because we have 3 unknowns and 2 equations, there will be some freedom in the solution anyway. So why not just kill this freedom straight away by setting one of the unknowns to some predefined value? Of course, you can argue, why didn't I choose 0 for that predefined value? But 0 is something we're not interested in, because if you choose 0, the rest will be 0 as well. And obviously, when they say find the vector, they mean find non-trivial vector, non-zero vector. That's why I just remove this uncertainty in the solution, this freedom in the solution, by setting one of the components straight away to some value, and this value is chosen non-zero to avoid zero solution.